Welcome to Brain Vision.
Our question says for part A that it wants us to use figure 47 to determine the magnetic dipole moment. And then we're going to go ahead and use that for part B and then use some stuff from part B for part C. So first we're going to find the magnetic dipole moment. Okay, so to calculate the magnetic dipole moment due to the non-conductive circular disk in the image, we have to first consider the magnetic dipole moment of the current carrying ring as follows. So the change in the magnetic dipole moment, d mu, where mu is the dipole moment, is equal to the change in current, di, times the area. Okay, well, this is equal to, the area is a vector, so this is going to be di times the area times the directionality of this, which is I hat. So here du is the magnetic dipole moments change, di is the current produced by the disk, and A is the area of the disk. So due to rotation of the disk, the charge distribution varies and it will produce a current. The magnetic field of the current can be written as di, or comes from the following. So di is the change in the current, which is equal to N times dq, the change in charge, where N is the number of oscillations per second, and dq is the change in the charge on the disk. And so the number of oscillations per second, N, is equal to the angular frequency, omega, divided by 2 pi, since it's rotating in a circle. So imagine that the disk then is divided up into a number of elementary thick rings, so a bunch of small thick rings. And let us consider that one ring of radius, say small r, and thickness of dr. So then the area of this small ring, dA, is going to be written as followed. We could say dA is equal to 2 pi r. Oh, forgot my 2. 2 pi r. dr. And the charge density of the disk we can call sigma. That's the common notation. Sigma here is equal to the charge Q divided by the area of the disk, A, where the area of the disk, A, is just simply equal to pi r squared. So the charge on this ring is equal to the product of the surface charge density and the area of the ring. So dq, and it'll make sense why we're doing all of this, because we're going to end up piecing all of this back together, because we need, if you go all the way back to our original expression here, we need di, right? Otherwise, we're not going to be able to solve for du. So we're trying to get di here, and we found that di is in dq, and so now here we are all the way down to figuring out what dq is and piecing this all the way back together. So dq is equal to sigma dA, but hey, we just found dA and sigma, so let's go ahead and replace those. So sigma here is q over A, or q over pi r squared, right? And dA we just found to be equal to 2 times pi times little r dr. Thus, we can plug this back into our expression to get di, because we said di was in dq. So let's get a new page going here. So now we have a better expression for di, where we know more of the terms. So now if we replace n with omega over 2 pi, because remember, if we go back, di was in dq. So an n was omega over 2 pi. And then what was dq? We just found dq. And that was equal to q over pi r squared, big R, not little r, multiplied by 2 pi little r times dr, or change in little r. Okay. So we can simplify this just a little bit. Let's make this a little simpler. This is Q omega r divided by pi r squared dr, d little r. Okay, so now we can substitute this back into our original expression for the change in the magnetic moment. So now we have d mu is equal to Q times omega times r divided by pi r squared. And this is big R, pi big R squared. And then we also have that dr, but I'm going to write the dr outside of every other term, because if you go back to du, it was di times the area A. But we just plugged in the di value, so now we need to plug in the area A, which we found to be pi r squared. So this is times pi r squared. And this is all going to be integrated with respect to dr, and this is going in the I hat direction. Okay, so now we can take the integral of both sides. So if we integrate both sides here, we integrate that side and we integrate this side. This side's getting integrated from 0 to the total radius here, big R. So what we find is we find mu, magnetic dipole moment, is equal to, well, if we go back to our expression above, let's simplify it before we take the integral. So that pi is going to cancel with that pi. And the two r's on top become r cubed. But q, omega, and big R squared are all constants, so they can be pulled out. So this is a very simple, easy integral. This just ends up being q times omega times big R squared, because we're integrating from 0 to big R, divided by 4. And this is all going in the I hat direction. So we can box that in as our solution for part A. Okay, part B says to determine the magnetic field at points on the axis at a distance x from its center. Okay, so to calculate the magnetic dipole moment due to the circular non-conducting ring at a distance x from the center of the disk along the axis, the magnetic field produced by the magnetic dipole moment has to be considered. And it has a magnitude along the dipole axis that can be written as follows. So let's start a new page, call this part B. And here, the change in the magnetic field, dB, is equal to mu naught times the distance little r squared divided by 2 times r squared plus the distance we are from the center, x squared. This all gets raised to the 3/2. And then this gets integrated with respect to di. And of course, the direction we're going is in the I hat direction. So again, x here is the distance of the point from the center of the disk. And we can substitute for di the q omega r dr over pi r squared that we had previously found, right? So if we go all the way back to di, we found, I'll underline this here in green, we found this expression for di. So let's go ahead and plug that in for di here. And what we end up with is this is equal to mu naught times r squared over 2 times r squared plus x squared to the 3/2. Let's extend this to make sure that's all in the numerator. And then now this is getting multiplied by what we just, the expression for di, which was q omega r dr divided by pi times big R squared. And of course, this is still going in the I hat direction. So we can simplify this just a little bit. And we're also going to integrate both sides. So we find that B here is equal to the integral of this simplified equation. And again, we're integrating from 0 to r, of course. Those are our bounds of our integral. And the simplified equation here gives us mu naught times q times omega. And then now we have r cubed because we had an r squared times an r term. So we have r cubed divided by 2 pi big R squared times r squared plus x squared, all raised to the 3/2. This is integrated with respect to d little r, all in the I hat direction. Okay, so you can pull everything out of the integral that isn't related to little r, right? So you will be left with the r squared plus x squared to the 3/2 because you can't get rid of the x squared there since it's inside that parentheses, which contains an r squared. But the mu naught, the q, the omega, the 2, the pi, the big R squared, all of that can be pulled out front of the integral. So what we're left with is r cubed over r squared plus x squared to the 3/2. That's a really tricky integral. You can do like an integration by parts. You can attempt to do it that way. You can use numerical integration methods, but I just used an integration table. There's no need to spend all your day trying to do a nasty integral. If it's an integration table, look it up and move forward. So that's what I did here, and we found that this integral is equal to mu naught times q times omega divided by 2 times pi times big R squared. That was everything that we had pulled out front. And then what was left from the integral, we have big R squared, because remember, it goes from 0 to r, plus 2x squared divided by the square root of big R squared plus x squared and then this all gets minused by 2x. And of course, this is still in the I hat direction. Sort of run out of room a little bit there, but I was able to fit it all in. And we can box that in as our solution for part B. Okay. And then there's one more part here. Part C, it says, does the equation 28.7b apply if x is much greater than big R? Okay. So if x is much greater than big R, we essentially want to know if it ends up simplifying to b is equal to mu naught over 2 pi times magnetic dipole moment mu over x to the 3rd. So we essentially want to see if it'll simplify to that. So again, if in the limit of x much greater than r, we need to simplify the equation for the magnetic field that we found previously. So in part B. So let's go ahead and write it out, and then we can start simplifying it. So I'm going to call everything in the beginning, I'll put it in this red bracket. I'm just going to call this our bracket, so I don't have to rewrite this over and over and over again. So what we're going to do is we're going to expand everything in the parentheses, not what's inside that red bracket. And then so on this page, when I rewrite things out, I'll put a red bracket, and that'll indicate what's supposed to be inside that red bracket. Okay, so we have B here is equal to what's in that red bracket times, and we have, I'm just going to simplify a little bit. So we have 2x. So if you go back here, we had r squared plus 2x squared. I'm going to pull a 2x squared out front. So we have 2x squared. And then now this is going to get multiplied by 1 plus r squared over 2x squared. And the reason I'm doing this is because I want to do a little Taylor expansion, and this is going to make that Taylor expansion more simple. And this is all divided by, now I'm going to pull an x out of the numerator. So if you go back here, we had square root of r squared plus x squared. So I'm going to pull x squared out. the square root of x squared is just x, so we end up with an x out front, and then inside we still have 1 plus r squared over x squared. So if you multiplied back through by x, you would end up with x squared plus r squared once again. And then this is minus 2x. Okay, so now we continue this a little bit. And so now our b here is equal to, I'm going to start doing a Taylor expansion of what's inside the parenthesis. We still have that red bracket group out front. And then inside the parenthesis, we now have 2x. So I simplified, I canceled the top and the bottom there a little bit. So I'm just going to simplify before expanding. So this is 2x multiplied by 1 plus, so maybe we should call this a bracket to distinguish it. So this is multiplied by 1 plus r squared over x squared raised to the minus 1/2, and then still minus 2x. So we haven't begun to expand yet, just simplified a little bit more. All right, so now we are ready to go ahead and do our Taylor expansion. Okay, so ran out of room there, so we'll do it on the new page. So this is equal to, you still have the red bracket group. And then our Taylor expansion gives us, you have 2x times 1 plus r squared over 2x squared times 1 minus r squared over 2x squared plus 3r to the 4th over 8x to the 4th plus, and of course you can just keep on expanding, but we don't need to do too many expansions. We'll just go ahead and stop there because, again, we're considering a situation where x is much greater than r. So eventually those x's on the bottom are going to overtake and those values are going to go towards 0. So we can ignore everything after that 4th order term. And then this is still minus 2x. Okay. So you'll notice that you have a 2x out front that you end up with, and then you're minusing a 2x out back, so those are going to cancel. And so what you end up with here is, and I'm going to go ahead and plug back in what I had in that red bracket. So we go all the way back. Remember, there's that red bracket term that we've been using. I'm going to plug that back in, and we have mu naught times q times omega divided by 2 pi r squared. That was everything in the red bracket. Now this is going to get multiplied by what was left. So if you notice here, we have the 2x term that gets canceled out with the minus 2x term. So let's see here. This term is going to cancel this term when it gets multiplied through by that one and that one. And then you have this r squared 2x cubed minus r squared, or excuse me, r squared over 2x squared minus r squared over 2x squared. If you multiply through by that 2x, that's going to cancel with that term. And all you're left with is this 3r to the 4th over 8x to the 3rd. Again, it's x to the 3rd because you had that 2x out front. And, or excuse me, 4x to the 3rd. And it's 4x to the 3rd because you had that 2x out front that got multiplied it. So one of those x's canceled and that became a 4. So we can cancel that and make it a 3. And then this gets canceled and becomes a 4 because it gets multiplied by a 2. So 1/8 times 2 is 1/4. So what we end up with here, all we have left is r to the 4th divided by 4r to the 3rd. Okay, so further simplifying just a little bit, what we end up with here is we have mu naught times q times omega divided by 2 pi. So that r squared cancels with the r to the fourth on the top. So you end up with r squared on top. Oh, and I wrote, I made a little typo here. I wrote r to the third. This should actually be x to the third. So that's r squared divided by 4x to the third. But if you remember, mu is q omega r squared over 4. So if we go, let's see how far back do we need to go. All the way back here. Yep. Right here we have mu is equal to q omega r squared over 4. Okay, so we can simply substitute that in for mu, and this leaves us with mu naught over 2 pi times mu over x to the third. But wait a minute. That is the 28.7b equation that we were trying to prove whether or not it would work. So yes, equation 28.7b does apply in this case, because that's what we ended up simplifying down to. So we can say yes, 28.7b does apply. Let's go ahead and box that in as our solution for part C in the final part of the question.